Hello everyone, welcome to this presentation about writing high-performance Delphi programs. My name is Primož Gabrijelčič. I'm a programmer, MVP, writer, blogger, and a lot more things. You don't have to write all my contact information down, just remember that you can surf to primož.gabrijelčič.org and you'll get all of my contact info there. I also write books, 3 published so far. One about parallel programming with Omnithread library, one about writing fast Delphi programs, the topic that we will touch but only slightly today, and the last one about design patterns in Delphi, how they work in connection with one another. One thing to remember, if you surf to www.thedelphigeek.com, that's my blog, and click on the presentations link on the right side, you will get a list of all my presentations with linked PowerPoint slides and code, including this presentation you are listening to right now. And on the same blog you can get access to my books if you want to read more about them. But enough about me. The topic of today is performance. So when I say high performance, what do I have in mind actually? Well, performance to different people has different meanings. It may mean maybe just running fast enough. For example, if you sit down and you type your code in the RAD Studio IDE, you want the development environment to be responsive to you, so you don't have to wait for it, so it doesn't block when you try to type something. That's one of the definitions. In other cases, for example, we just mean the raw speed of the program. For example, a database query, a long database query is never fast enough, and as fast as you optimize it, it will always be too slow for some users, and you will always be striving for more raw speed that you can pull out of your code. And on some other occasions, for example, by responsive we mean that the server responds to our queries in a reasonable amount of time. So we are back in the fast enough area. So when you go to some HTTP page and you click a hyperlink, you want your result back in, let's say, half a second, not 20 seconds or something like that. To get good performance in different occasions and different scenarios, you will need different tools. For example, to get good performance out of a server, you need to introduce parallel processing and other tricks, database caching, request caching, and so on. To get fast enough performance from a desktop application, you maybe need just some careful code writing and not doing stupid things. So there's no silver bullet, there's nothing that will give you performance in a small pill. And there are different ways with which you can achieve better performance. So my advice is go with this checklist. So first, and always the first step, is to confirm the problem. Measure the code. So if you suspect something, put a manual timing into the program called tStopWatch or query performance counter or get tick count or whatever, just measure. Even better, use a profiler. Use AQTime or use ASM profiler or any of other tools that are available there for Delphi. Then, when you are pretty sure where the problem is, the best way you can approach is to fix the algorithm, because with this you will get the best performance enhancement. If that's not a possibility, then you have other options. You have fine-tuned the code, so handcraft some parts of the code so that they will run faster than before. You can introduce parallelism to your code, and by that also introduce a big source of problems. You can use external libraries which may solve your problem faster than you can solve it, but then you will have problems if they are not maintained anymore, or if you have to write some code to glue this library into your program, or as a last case, rewrite it in assembler. But I can promise you that the future you will hate you very much for this choice, because in 10 years something will have to be changed and nobody will remember what that assembler code does anymore, and you will have to fix it. And don't go there. Really, you will hate me if you go there. But for today I will just fix on one item in this list, maybe the item where I can give some advices which will give you a very fast improvement in your code. So there will be a best bang for the buck maybe. And that's fixing the algorithm. And we'll again focus on two different ideas here. One, when you have to fix a slow algorithm, find a better one. And to give you an idea of what I'm talking about, I will show a short example of how a simple change of an algorithm can bring a big performance increase in the code. And another advice which seems weird at the first is, if the code is slow, well, run less code. If you run less slow code, then the program will be faster all in all. And we'll come to that in the second part of the presentation. First, choosing a better algorithm. So when the computer scientists talk about algorithms, they always introduce something called algorithm complexity. So when computer scientists start to talk about algorithmic complexity, they typically pull in a big O function, it is called. So it's this one, O. And they will say, this algorithm behaves with O of, and they then will give you some complex expression after it. There are strong mathematical ideas behind this O of something. We don't have to know them, promise you that, because we can explain this O function very simple. It will tell you how your program will slow down when you put in more data. Because typically we programmers test on small data sets, because someone has to generate those test data sets, and we don't bother. We just put few numbers in and then we say, oh, it works fine, let's move on. There are other problems that have to be fixed. And then the customers come and then take our code, and then they put 10,000 times more data in than we did. And sometimes this will cause problems, sometimes it will not. And this O of something is exactly the function that will describe what will happen when you put more data into a program. So on the best case, we have something that's called O of 1, or constant function algorithms which simply don't get slower. So when you access something from an array, this will take the same quantity of time, the same duration, if this array has 10 elements or 10 million of elements. well, forget now bringing those data into the CPU cache and such details. I'm talking in general terms. Then next very typical example is O of n. If you have n elements and you want to find one and they are not sorted in or something, you have to check them one by one. So in the worst case, you have to check all n elements to find the correct one. So linear search is, we say, is of order O of n. When you are searching in ordered list, you can use bisection. You can split the list in half, check in which half the element is, split the rest of the list in half, and so on. And this algorithm will be much faster. It will be find your result in logarithmic time, we say. And if you don't think there's not much difference, well, there is some difference. If you check the graph on the right, I have here a small data set growing from 1 to 20 and different complexities displayed on it. So logarithmic function grows very, very slowly. It's almost constant, goes slowly up, while linear function grows quite faster. And we'll see later this difference in practice. And then we have square function, very typical in code, O of n of 2, which means if I put in 10 times element more, the code will be 100 times slower. As you can see in the graph, 10 times element more, 10 times more elements, 100 times, that's 10 to the second degree, slower code. And this one grows faster and faster and faster. That's how bad sorts behave, the one that we can all type from our head, like bubble sort. If we implement a better sort, it will behave in n times logarithm of n time, which is a function which grows close to a linear, not as good as O of n, but not as bad as n squared. Again, we'll see an example of this. And the last example I have here are exponential functions which simply explode. You will just be able to calculate them for very, very small data sets, and you should stay away from them. Again, they will come later in an example. Two links I would like to point to you. bigocheatsheet.com has a nice poster listing all different algorithmic complexities and how fast some data structures behave when you use them, while geeksforgeeks.org has a very, very good and long discussion and comparison about different data structures. Much recommended. Okay, so let's switch to code now. I have here a demo program called Random Word Search, which implements a search for a random English word in a very weird way. So, stupid program gives a better demo. First, it generates a random word, and the function to generate a word is really, really simple. Just concatenates together random characters, and then it calls some helper function find in dictionary, which is parameter to this find good word, and this dictionary checks if this randomly generated word can be found in a dictionary. And this whole code, this loop terminates when the word is found, or when the check-in took more than 10 seconds, because that is as long as the customer is prepared to wait for our code, and give us a result at the end. So let's see what happens when I run this program. The dictionary contains 370,000 words, and my first implementation uses simple search in unordered list. I told you before, this is O of n. So my list has 370,000 words, and in the worst case, all of them have to be checked. And for words of length 4, this works perfect. Fast responses, words are found very quickly. But if I bump this up, program starts to behave slower. 5-letter words took 2 seconds, 4 seconds. And if I go to 6-letter words, I will start getting some timeouts. Yep, immediately. So what does my list button do? So it has a simple string list, F words unsorted, which contains all words from the dictionary. And it runs an index of function. And when the list is not sorted, this index of just checks the first element, second element, third element, and so on. So, how to make the code faster? First idea, change the algorithm. Find a better one. I told you before that unordered search has O of n, and search in an ordered list has big O of logarithm n. So, and I claimed that that is quite faster. Let's see. I have here a sorted list of words, and for a second, trust me on that. And I will use again index of, but index of on a sorted list uses bisection in Delphi RTL, not a linear search. So on 4-letter words, there's not much difference, because the code was already fast before. But if I go to 6, there's a big difference. I can find 6-letter words with this code. I had problems with 6-letter words before. Even 7-letter words work. But if I try to find something longer, again, I start hitting the limits of my search algorithm. Again, it becomes too slow. Okay, remember this, 8 letters. Let's find a better algorithm. In Delphi, we have something called a dictionary. And we can put words into dictionary, and we'll see this in a moment. And then we can ask the dictionary, do you have this word? And this contains key function actually works in linear time, or something very close to it. It is not as fast as lookup into an array, but is again faster than the index of when the dictionary or the list are large enough. Let's prove it. So dictionary works great for 4 letters, works great for 6-letter words, works okay for 8-letter words. Well, okay-ish, but if I go higher, again, I will run into problems. So, what can I do now? My algorithm uses the fastest or something close to the fastest possible search. And if I want to find a better algorithm, I can maybe revisit my original idea that finding a word is composed of 2 steps. First one is generating a word, second one is checking the word. For example, I could just look up the word in the dictionary. But how will I get a random word of a specific length? Well, there are different approaches, and I'll just show one here. if we check the loading function, so this load words is called the program startup, and the parameter is list of those 370,000 English words, which was just loaded from a file. And to search in an unsorted list, we can just put list into this word list into a string list, and we're done. To search in a sorted list, we have to put the words into a string list and then sort it, which takes some time. As I said before, it's in order of n times log n, but we are only doing it once. If when we are looking for a word, we are doing it many times. So it helps if we take some time in the beginning, prepare everything, and then run a faster algorithm. The third one, the dictionary, creates a dictionary of strings, and actually the value of our parameter is not so important here. I'm just putting in a boolean. I could use anything. And then we put every word in the original list into this dictionary. This is again more preparation than just sorting a list, because all kinds of things happen here behind the scene. But after that, we have a faster search. And the last one actually uses one list which contains string lists. So, and it works like this. We take a word from the word list, and then we check the length of this word. If we already have a list of words of the same length, we do nothing here, and we just put the word into this list. Otherwise, we extend our list of lists with empty string lists until we reach this specified length, and then we have our target string list ready in this larger array. So at the end we will have words list of list, which will have a string list and string list, and maybe near the end there won't be any word with length, I don't know, 36, but there will be a word or more with a length of 37, like this, and then it will end. And then my lookup function just says, okay, get me the length of the word, check if there is appropriate t-string list in the larger list, and if there is, pick a random number from 0 to number of elements in this list. And if we have this list and we have the random number, we just put out the word. If we don't have the list or we don't have the random number, we just report an error, no such word. And we can do all of this in pretty much 0 time. So we spent quite some more on preparation. We used more memory because there are multiple string lists here, but result, this works as fast as it could work at all. So nothing of length 30, interesting. Let's check some shorter words. So don't be happy with the first idea which springs into your mind, searching into a string list in this example. Think some more, maybe you'll get a better idea later, and it will be faster. Let's now give some thought to my second idea of improving the speed of your program, running less code. And I give here two very controversial statements maybe. One says if a part of a program is slow, don't execute it so much. Well, duh. It's slow, don't execute it, sure. And the second says if a part of a program is slow, don't execute it at all. Okay, yes, makes some sense, but we want the program to be functional at the end, not just remove the slow code out of it. So these are not brainless ideas, they just try to bring across a concept which I'll be talking about, which is of reducing the, well, running less code. So what can you do to don't execute so much code? In a typical visual application, first idea, don't update it thousands of times per second. If there is a background process which is monitored, if there is a hardware which is monitored, maybe you don't have to display every change on the screen. If you are enumerating folders and looking for files in the folders, well, maybe don't display every file name on the screen. If you are browsing the web and by some luck the connection is very, very fast, maybe don't display every URL on the screen. Your users can't process that amount of information anyway, and it can make your program much slower. And I'm ready to prove that. So for my second program of the day, I will run this progress bar exe, click the test 1 button, and you can see that something is going on, and this something takes 6 seconds. Well, it's not great, not terrible, but let's see what's going on behind this button. So this calls show message, okay, and displays result of some function, okay, and it's a documented function because I'm a nice guy. And this function simulates reading from a 2 GB file in very, very small blocks, which is, I must say, typical for a code which started its life in Delphi 2.0 files and then got upgraded through the years and is still functioning in modern age, but nobody really touched it and gave it some love. So this code uses a progress bar to display the progress, and it displays the progress by setting the maximum value to file size, which is 2 gigabytes, position to 0, and then starts the simulation and says while we are in the file, we will pick the block size and then we will read the block. And in our example, this reading takes 0 time actually, so this should be quite fast. And then we update the progress bar by putting it into position. Okay, so why is this slow? I'm claiming that it's slow because this progress bar gets updated about 2 million times. And I can measure it. I can put a stopwatch across this, or I can just disable this code. Click my test button again, poof, and we are done. So yes, updating user interface 2 million times in 6 seconds is slow. What can we do? We fix the algorithm. No one can see that this progress bar was updated 2 million times. No one has the accuracy on the screen to see such small changes. So users are typically quite happy if we show them percentage from 0 to 100. And this code does exactly that. It sets maximum to 100, current position to 0, reads from the file as before, and then calculates the current percentage of the progress. So we are total bytes out of file size into the file, and we multiply this by 100 and round. and only if this is different than the last displayed percentage, we will update the progress bar. So for the price of some more code, we will only update the progress bar 100 times, not 2 million times. The result, oh yeah, it runs in 13 milliseconds, and it's not a fluke. It runs 13 million or 15 or 12 or whatever milliseconds every time. So that's one way to execute less code, run less user interface updates. The second idea, before updating the user interface, call begin update and end update after you finish the updating, of course. And let's see my example here. Begin update. This is a VCL application. You also have begin update FMX in the demo package, so you can compare the numbers between them, but I'll focus on this one. This application adds a bunch of lines to a list box, and after that it adds the same lines to a memo, and we'll have to wait because there are, I believe, 10,000 lines, and adding 10,000 lines one by one takes some time on Windows. And that's because when we add a line, for example, to list box, VCL will send a message to the Windows control. It will respond with something, then the VCL will send another message to the VCL control, to the Windows control, sorry, and it will respond with something, and for each edit line about 7 messages are sent to the Windows, and this takes a long time, as you could see. So for 10,000 lines, we needed 7.5 seconds for listbox and 29 seconds for the memo. So let's see the code. Well, again, I have a testing function all around. It just measures times and displays results. But the workhorses are here. The first one adds 10,000 lines to a list box. The second one adds 10,000 lines to a memo. And I claim that if I wrap this in begin update, end update, this code will be much faster. And that's because the VCL knows that it is in updating state, and when you do the add, it will not send all those 7 messages to the Windows control and back. Only when you call end update, the VCL will update everything on the screen. Let's prove my words. As I said, always measure. Measure first, then measure your improvements to make sure that your code is not slower suddenly. So we had 7 seconds and 29 seconds, and we are down to half a second and 3 seconds. So this is much better. Can we do better? In the list box case, yes, and I will show this with the second demo. In the memo case, also yes. So in this, I will show this in this demo. So what can we do with the memo? Well, we can construct our content in advance. We can add all those lines into some intermediate object. I have a string list here. And then just in one go, take the text of this string list and push it into the memo, which will be only few messages, Windows messages. So again, add text, poof. This took only 125 milliseconds. Now that's an improvement, huh? So the last idea here is, yes, I will return to listbox, I promise. But first something else. The last idea on the don't execute is so much list is don't send around millions of messages per second, which is just a variation of the first line, but it applies to multi-threaded programs. So when you do multi-threading, one of very frequent traps is that you want to notify main thread about what the background threads are doing. And if background threads are doing some long processing, then you want to just send status updates for every small update, just what we did in the what we did with the user interface with the first example. Well, don't do that. Again, accumulate the changes, send them only a few times per second or in small batches, or however you can split them up. Otherwise, you will bring your system to the halt. So on the second idea, don't execute it at all. How can you make your program fully functional but without executing the slow code? Two ideas I'm talking about today. First is virtualization of the user interface, which means use components which won't process stuff that is not visible on the screen. Two very useful components for this: virtual list box, which is just a flag in the tListBox component, and virtual tree view, which is a great powerful component, but I won't go into it today. And I will return to the second idea, memoization, later. First, the virtual list box. So if I return to this code for a second, even in this second case, when we wrapped everything between begin update and end the update, the list box ended up with 10,000 items inside. Sorry, wrong program. I will switch again. So this list now has 10,000 items, and if I scroll to the end, I can promise you that I did not saw all 10,000 on the screen, because when I moved my scroller around, the window jumped between one number to some other number of line, and it skipped some 1,000 or 3,000 or 8,000 lines in between if I'm fast. And no user will check all those 10,000 lines in such a record. So I don't have to actually have them there. I just want them to be available on demand. If the list box says, okay, I need line 1, someone has to provide line 1. If the list box says, okay, I need line 4099, someone has to provide line 4099. And that's the idea behind virtual list box. And I hate when buttons move around in my VCL application. So my virtual list box is only a list box, not a memo. Only one button, and this one button again adds 10,000 lines to my list box, and it does it in practically 0 time. So it takes 7 milliseconds to add 10,000 lines to a list box. But that's because they're not really here. Only lines 1 to 18 are here. Other lines are just somewhere in some background storage. And if I jump around again, no one actually generated lines 6,000 to, I don't know, 100 to 6,000. I don't know which were visible and which not. So what goes on here? Well, firstly, I switched the style property of this list box from normal LB standard to LB virtual. And there's also virtual owner draw if you want to affect how the the lines I'm drawn on the screen, but this is a different topic. Second, list box has 3 events: on data find, and on data object. I have to write on data because this event handler actually gives me values from these lines. I have to write on data find if somewhere in the code someone uses listbox.items.indexOf function to find something in my list. And I have to write on data object if the code is attaching objects to my list box. In this example, I just provided the first 2, but only the first one is actually used. And let's see how this works. So when I fill my virtual list box, I'm actually generating data for some backing storage. Virtual list box will typically be connected to some model or to some backend storage, something like that. And in my example, I just am using a string list, and I'm putting my 10,000 lines inside the string list. And then I will say to the list box, hey, you have 10,000 lines, that's it. And when the list box wants to paint line 1, it will call my onData event handler, and it will say, hey, I need line number, well, 0 is the first one, of course, not 1. And my code says, okay, model, give me the 0th line and return it in this data parameter, and listbox will put it on the screen. Similarly, if somewhere in the code someone calls listbox1 index items index of ABC, the listbox itself will call this on data find event, and I can do this search inside the listbox. Remember, my listbox doesn't know what its data is. I have to provide the search. And if you want a proof, let's see what we can do. We can, for example, log everything to the event log. And we just log the line number that is requested to the event log, and we'll see then which line numbers were requested. Let's run this. Okay, I did something wrong. Oh, of course, I don't need to format here. That's just my habit. Add them, and let's check the event log. So actually, only lines from 0 to 18 were requested. And let me now quickly jump to the end. You can see lines 300 to 318, then 736 to 754, 1609, 1627, and so on. So most of the lines were not displayed as I claimed. So don't execute it if it is slow. Find some way to remove this code, to ignore it, to not do it, whatever helps you. And for those occasions when you don't know how to fix the algorithm, don't know how to not execute something, maybe look into caching. Maybe your code tries to calculate a value for something more than once and is slow because of that. Maybe it calculates some value like 10,000 times, and that makes it slow. Think about caching as introducing a local variable. So I don't know, in my previous code, where's my random word search? I have this find good word fast function, and it says word length becomes input word length.value. My input word length is this spin edit, and again input word length.value, and again, and actually it calculates the same value 3 times, and each call sends at least one message to a Windows control to get this value back. So I could use here a word length, which I actually started to introduce caching to my code, but then I didn't fully implement it because I was distracted, most probably. But now I can fully implement my caching. It was used here, it was used here, and now actually I do calculate this word length only once, and most of the legacy code looks something like my previous version of this function. Something is optimized, something is not. The code is called many times, the code is calculated more than once, and so on and so on. But just to prove that this actually helps, let me show you this example. So my typical example for memoization is calculating Fibonacci numbers, or numbers in the Fibonacci sequence. So there's the sequence which goes 1, 1, and then every number is a sum of the previous one. 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. And this implementation follows the definition, says if this is one of the first 2 elements, then it is 1. Otherwise, get the element before that and get an element before the previous element, and then add them together and you will get the result. This is an example of an exponential algorithm, which goes very, very fast, and it may not be obvious at the first glance. For example, my Fibonacci, well, let's start with 1. So I set it's 1, 1, 2, 3, 5, 8, 13, and so on. So if I want to get 20th element, well, that's extremely fast, still extremely fast. What's your problem actually? Well, my problem is that, I don't know, at some point it starts to behave very slowly. So suddenly we are at 3 seconds. Let's go 2 elements up. Okay, now this is actually not the program which behaves in the doctrine of don't make the user wait for the result. It's now 8 seconds. Just one more because I will not go up higher. I have to wait, and I have to wait, I have to wait like 13 seconds and so on, and it will explode. This algorithm can calculate somewhere up to 90 seconds or something like that. Element will check later. After that we run out of int64 data type, but I will certainly not try to calculate this value with this algorithm, because I will have to wait up to the end of the solar system or even longer. So what's the problem here? The problem is that this stupid implementation, of course, it's always the fault of the algorithm. It says, let's say I want to calculate 6th element. It says, okay, calculate me element 5 and element 4. Okay, but to calculate element 5, I have to calculate element 4 and element 3. And to calculate element 4, I have to calculate element 3 and element 2. And to calculate element 4, I need element 3 and I need element 2. And for element 3, I need element 2. I need element 1. Okay, I need no. Okay, actually, I know element 2 is 1. So this is where it stops. For element 3, I need element 2 is 1. And for element 2, I know it is 1. So I can now go back and put those two together. Get 2. Put those two together. Get 2 and so on. But the problem here is that I have to calculate the same value multiple times. So I calculate element for index 3 at least 3 times, and element index 4 2 times, and so on. And if I don't know how to be smarter and put in a better algorithm, I can use memoization or caching. And caching says, okay, I have a table of results. I know I can only calculate like 90 something of them, so I don't need a large table. I'm having here a dynamic array sized to an appropriate value. If I need elements 1 or 2, I will return 1. This is as before. If I need some other element, I will call this same function recursively, just as before. But immediately after I learn what some element is, I will put it into the table. And then I will fetch it from the table next time this function is called. So what happens now for element 5, this says I don't have element 5, calculate 4 and 3. I don't have element 4, calculate 3 and 2. I don't have element 3, calculate 2. Okay, this is... Okay, at this moment we already know this is 1. Calculate 2, this is 1, and element 1, which is also 1. Okay, so now we know this part. For element, and we can say, okay, element 3 is 1 plus 1 is 2, and we put it in the table. And now the second part, this one, this was all inside this call. The second part says, okay, what's the value for element 3? Oh, I have it cached. And just pulls it up. Yay! And we can now put everything together. And this works. It's a simple change to the code. And it is very, very fast. So we had problems before, somewhere at 644. Hey, works. 90. 91. No problems at all. So of course you can be even smarter and introduce a better algorithm. I have here an iterative solution, not recursive, which just starts with 1 and adds elements together. And it's as fast as it goes. But sometimes you will not be able to improve your code in such manner. And in such cases, memoization or caching may be a better solution. So in this case, I just used a simple T-array. But in some more complicated cases, you may want to use my TGP cache, which is a generic cache. It's actually something similar to a limited size dictionary. Uses a key and a value, and it's very, very fast. It runs in linear type on all operations, and you can get it at GitHub. So check the code. It's very easy to use. And that's it for today. If you want to learn more, I can recommend a few books and online resources. Julian Bucknell wrote great algorithms and data structures, sadly a long time ago, so the book by itself is relatively obsolete now, but still contains many great ideas and explanations. And then there's my Delphi High Performance, which has the advantage that it is written for a modern Delphi. And on non-Delphi side, Robert Sedgwick and Kevin Wayne wrote excellent book, Algorithms, with one downside: it has examples in Java, but it's still a great book. And it has a great online edition at Princeton Edu with all example and all texts and everything. Then you have different courses at every course provider, and you can get a lot of information at Geeks for Geeks site under the topic of data structures or fundamentals of algorithms. And at the end, if you have any question, find me on the Delphi Praxis forum, preferably on the English site, because my German is practically non-existent. So that's it from me today. Thank you for listening. If you have any question, well, I'm waiting for them now.